Welcome to this session. In this session, we are going to derive the general formula for solving linear homogeneous recurrence relations with constant coefficients. So let's go into the class. So solving linear homogeneous recurrence relations with constant coefficients. So consider the recurrence relation, the linear homogeneous and say degree k or order k given as an equals to c1 an minus 1 plus c2 an minus 2 plus c3 an minus 3 up to plus ck an minus k. And the condition is that ck must never be 0. So this is the equation with whose solution we would like to discuss in this session. Now, let's call this equation, let's call it 1. Let's call that equation 1. So to solve equation 1, we assume that 1 has a solution of the form an equals to r raised power n. So let's assume that the solution to equation 1 is an equals to r raised power n, where r is a constant. Now, you see, if you define an equals to r power n, then an minus 1 will be given by r raised power n minus 1. Then an minus 2 will be given by r raised power n minus 2. And then an minus 3 will be given by r raised power n minus 3, all the way up to n minus k will be given by r raised power n minus k. It follows from this result. Actually, we can write put implication sign here, that an equals to r raised power n implies that all these other terms can be defined in this manner. So therefore, if I call all these relations, I call this one 2. So replacing 2 in 1, we have So where there's an, I replace by r power n. Where there's an minus 1, I replace by r raised power n minus 1. So next term will be C2 r raised power n minus 2. Next will be C3 r raised power n minus 3 plus up to CK r raised power n minus k. So those will be the substitution of 2 in 1. So taking everything to the left-hand side of this equation, I'll get r power n minus C1 r raised power n minus 1 minus C2 r raised power n minus 2 minus C3 r raised power n minus 3 minus Ck r raised power n minus k is equals to 0. That's what I get by taking every term on the left-hand side. Now, since actually this r is a non-zero constant, so since r is non-zero, then divide each term. So let's call this one equation 3. In 3 by r raised power n minus k. i.e., so I'll have r power n over r raised power n minus k minus C1 r raised power n minus 1 over r raised power n minus k minus C2 r raised power n minus 2 over r raised power n minus k minus C3 r raised power n minus 3 over r raised power n minus k minus Ck r raised power n minus k over r raised power n minus k equals to 0 over r raised power n minus k. This division is possible because the value of r is not 0. So then loss of indices, this is the same as r raised power n minus k. So the same as r raised power n minus k is plus k. So this would be just the same as r raised power k. So this first term will give us r power k. So this will be r power k minus C1. And this one, the same thing, loss of indices. So it will be n minus 1 minus n minus k, which is the same as n minus 1 minus n, minus is plus. So n minus n, so minus 1 plus k is k minus 1. So this will be r k minus 1 minus C2. This will be n minus 2 minus n minus k. So n minus 2 minus n, minus is plus. So minus and plus cancels out. So this will be k minus 2. R raised power k minus 2. Similarly, this other one will be r raised power k minus 3 minus other several terms. Up to minus, so this one will just be ck because this and this is 1 equals to 0. So this is, let's call this one equation 4. Call this one equation 4. This equation 4. Now, equation 4, when you solve this equation in 4, which is an equation of degree k, then we find the values of r, different r. So equation 4 is called the characteristic equation whose solutions are called solution is called characteristic roots. So 4 is characteristic equation and the solution are called characteristic roots. So characteristic equation of the recurrence relation, and then the solution is characteristic roots. So given that the roots of equation 4 are distinct, i.e. we have R1, R2, R3, up to Rk, then the solution of the recurrent relation 1 question 1 is this question here we gave as the linear homogeneous recurrent relation of degree k. The solution of equation 1 is an is given by alpha 1 r1 power n plus alpha 2 r2 power n plus alpha 3 r3 power n plus up to plus alpha n alpha k r power k rk power n. So this would be the solution for that given question 1, assuming that it has r different roots, rk different, it has k different roots, r1, r2 up to k. So the case, if we have just if k, this one observation, so this one, number 2, if k is 2, then 4 becomes this equation 4. So put 2 here. So we'll have 2 minus 1 is 1. So we'll stop at this point here. So it'll be r squared minus c1r minus c2 equals to 0. Let's call this one equation 5. And then case 1, if R1 and R2 are distinct roots, of 5, then the solution of, I remember if k is 2, 4 becomes this equation, and it's the same thing as saying the original equation was given by an equals to c1 an minus 1 plus c2 an minus 2 equals, that's the original equation from which characteristic equation is obtained from. Then the solution is an equals to alpha 1 r1 power n plus alpha 2 r2 power n. And then second case, if case 2, if r1 equals to r2, then, or just the same as the root of this equation 2, then the solution is an is given by alpha 1 r raised power n plus alpha 2 n r raised power n. So that's what we have in the case of a repeated root. And then case 3, if r equals to alpha or a plus bi plus or minus, this is a complex root, then solution will be an will be alpha 1 a plus bi power n, and then plus alpha 2 a minus bi power n. So this will be the solution for the case of complex roots. So in the next session, we'll do examples to see how to solve a linear recurrence relations with constant coefficients. Thank you.